Welcome to the second lecture of Chemistry Lovers Organic Chemistry course. And in this lecture, we will be discussing about the basics of stereochemistry. In the first lecture, I have discussed about the chemical bonding and molecular structure. And if you didn't watch that, I will highly recommend that you first watch that video and then come to this lecture. So here we are going to discuss about the basics of stereochemistry and different projection formulas. First, we will discuss about molecular symmetry and point group because this is very important. You have to understand the symmetry elements present in a molecule and different symmetry operations in order to understand the stereochemistry overall. So that we will discuss first. So if we talk about symmetry, what is symmetry? Symmetry is basically when you rotate a molecule or when you get a reflection of a molecule, if you get the same kind of arrangement, then we say that symmetry is present in that molecule. So we have several kind of symmetries. So the first symmetry which we will talk about is the symmetry of axis, that is proper axis of symmetry or simple axis of symmetry. What is mean by that? So if you have a molecule and if you rotate the molecule through a particular axis, and on doing so if you get the similar arrangement of the molecule, that is after the rotation you cannot distinguish between the two arrangements, you think that these two are same, then this is called symmetry of axis or proper axis of symmetry, and this operation is called proper axis of symmetry. So I can make you understand with this model. So this is our model, you can see this is our model. So let's say this is your boron and all these blue atoms, they are fluorine atoms. So this is BF3 which is represented in the slide also. So now if I rotate the molecule by 120 degree, I will get a similar arrangement. You cannot distinguish between this one and the previous one, right? So that's why we say that this molecule is having a symmetry axis, and because it is obtained by rotation of 120 degree, so we divide 360 by 120, so we get 3. So that's why it is called C3 axis. Okay, so it is called C3 axis. So that is also shown in the slide, you can see. So BF3 molecule can be rotated by 120 degree and we get the same arrangement. Basically three different arrangements are possible, but they are indistinguishable, right? So we call it C3 axis. This is called proper axis of symmetry or principal axis of symmetry. Now if you look carefully, there is another proper axis of symmetry in the molecule. So we can rotate the molecule like this also. Okay, if we rotate the molecule like this, then also we get a similar arrangement. You cannot distinguish between the two. So I am saying like this. Yeah, so the same is shown in the slide also, you can see. So now we are rotating by 180 degree, right? So if we divide 360 by 180, we get 2. So that's why we call this symmetry axis as C2 symmetry axis. So BF3 molecule has one C3 axis and 3 C2 axis actually, because along every BF atom you can imagine one C2 axis, right? So it has 3 C2 axis, and not only so these are not only a general C2 axis, they are actually perpendicular to the C3 axis. So this C3 axis we call it principal axis. Okay, why we call it principal axis? Because uh, it is of higher order. So one is C3, another one is C2. So 3 is greater than 2. So because C3 is of higher order, we call it principal axis, and the other axis, that is C2, is called uh, secondary axis. Okay, and this C2 is actually perpendicular to the C3. So this is very important. So if we talk about axis of symmetry, BF3 has two symmetry axes. One is C3 and there are three perpendicular C2 axes. Now let us talk about symmetry of second kind or symmetry of second order, and three symmetry elements come into this category. One is plane of symmetry, another one is point of inversion, and third one is rotoreflectory axis. So first we are talking about the plane of symmetry. So here for the illustration purpose we took the example of PCl5. So the PCl5 you can see. So in case of PCl5 there is a similar kind of plane like the BF3 molecule. So that there is a molecular plane, and this molecular plane is actually bisecting the molecule, right? So that's why, so if you look at the two sides of the plane, two sides are similar, so that's why we call it a symmetry plane, right? And it is called sigma horizontal. So every symmetry plane is called sigma plane. Now it is called sigma horizontal. Why? Because if you look carefully uh, along the axis, that is Cl PCl bond, along the Cl PCl bond on the axis there is a C3 axis, same as BF3. If you look at the PCl5, so there is also a C3 axis present in the PCl5 molecule. And the sigma plane which we have discussed, that sigma plane is actually bisecting the C3 axis, or actually perpendicular to the C3 axis. So we call it sigma horizontal or sigma H. If you look at the right hand side, three other symmetry planes are present in the PCl5 molecule, and they are actually bisecting the molecule, but they are not perpendicular to the C3 axis, rather they are parallel to the C3 axis. You can see in the picture we have represented three sigma planes, and these sigma planes, as they are parallel to the C3 axis or principal axis, so we call them sigma vertical or sigma v. So when your sigma plane is perpendicular to the principal axis, we call it sigma h, and when it is parallel to the principal axis, we call it sigma v. So this nomenclature is very important. Yeah, so in the next slide we have shown that, right? Yeah, and also the two sigma planes, the sigma v planes, they are actually bisecting the perpendicular C2 axis. Okay, this is very important. They are bisecting the perpendicular C2 axis. Now so, and if you look at the BF3 molecule, in the BF3 molecule also these symmetry planes are present, sigma v and sigma h, they are present. You can look very easily. Okay, now the next symmetry element is called point of inversion of center or center of inversion. So in this case, so if we take a molecule and if we take the center of the molecule, then if we go from the center to any particular direction, and if we come back and go to the opposite direction with same magnitude, then if we get similar kind of point, we call point of inversion is present in the molecule, and it is illustrated with the example of benzene. So in benzene molecule we can take the center of the molecule, and if we go any direction and if we come back to the center and go in the opposite direction with the same magnitude, then we get similar point. So that's why point of inversion is present in the molecule, right? Not only benzene, there are many other molecules where point of inversion is present. I am giving you a task. Find out 5 different molecules where point of inversion is present, and let me know in the comment section. Now the next symmetry element is called improper axis of symmetry or roto-reflectory axis. It is also represented by SN. So as the name suggests, it is roto-reflectory. So rotation and reflection both are present here. So for the illustration purpose, we have taken the example of ethane molecule. Okay, and the ethane molecule is in the staggered form. What is the staggered, what is eclipse, I will discuss later, but you just look at the slide. So we have taken the ethane molecule, and now if we rotate the molecule by 60 degrees, so this is our ethane molecule. Let's say I am showing you with the with the model. This is our model. Yeah, so this is our ethane molecule, and we actually, so yeah, this is like this. So we are rotating the molecule whole, not along the bond. We are rotating the whole molecule. We are rotating the whole molecule, not along the bond. So if we are rotating the molecule by 60 degree, not along the bond but whole molecule 60 degrees. So this is called C6 axis or C6 operation, because if we divide 360 by 60 degree, we get 6. So this is a C6 axis, C6 axis of rotation. And then if we take a reflection of the molecule which we get after the rotation, and we place the mirror perpendicular to the axis of rotation. This is very important. then we get the same molecule what we have in the initial phase, right? So first we take a C6 rotation, and then we take a reflection along the plane which is perpendicular to the C6 axis or the principal axis, and we get the same arrangement at the previous one. So basically we are getting a symmetry, and because it is a symmetry operation which is first rotation and then reflection, so it is called rotoreflectory rotation, and it is obtained by multiplying C6 into sigma h. In this case it is sigma h, the plane is sigma h plane, horizontal plane, because it is perpendicular to the principal axis, and it is called S6. Similarly, in the same molecule S2 is also present. In the right hand side you can see S2 is also present, because if we take 180-degree rotation of the molecule and we take the mirror image or the reflection of the molecule, we will get the same arrangement. So S2 is also present. So this is called rotoreflectory axis or improper axis of symmetry. Now in the molecule, if you look carefully, point of inversion is also present. So if we take a point here at the middle and we go at this direction, we get this hydrogen. Similarly, so from the center, if we now go to the bottom here, we get the hydrogen. Similarly, if we come here, we have one hydrogen, and in the opposite direction, if we go there, we have one hydrogen here. Similarly, if we go from middle to here, we have one hydrogen, and in the opposite direction from here to here, we have another hydrogen. So point of inversion is also present, and we can prove that if a molecule contain S2, it will also contain point of inversion or I, and that is also that can also be proved through the Cartesian axis. So here we have the P point, we are rotating the P point along the Z axis, and we get the P prime point, and the coordinate of P prime is now minus x, minus y, and z. The z axis is unaltered because we are rotating along the z axis. Now if we get a reflection, or if we get a reflection of the point P prime, and we set the mirror at the xy plane that is perpendicular to our axis, then we will get the point Q, that is minus x, minus y, minus z, right? So if you look at the relationship between P and Q, what you will get? So P, the coordinate is x, y, z, and for Q the coordinate is minus x, minus y, minus z, right? So that's why it is basically a point of inversion, that is the opposite point. And also what we have done, we have first we did a C2 rotation, and then we take a reflection along the perpendicular plane, right? So we basically do a S2 operation. So we can see that S2 operation and point of inversion operation is giving us the same result. So that's why we call S2 and point of inversion equivalent, right? So we can easily prove that. Now our next thing is, so now based on the symmetry elements present in a molecule, we can classify the molecules in different point groups. So the rules are written here in the slide. You can see the rules are written in the slide one by one, and by following this rule you can classify molecules in different point groups. So if you know the point group, you can easily say what the symmetry elements present in the molecule. So first of all, if a molecule has only C1 axis and nothing else, that is the molecule is devoid of having any symmetry, then it will fall into the category of C1 point group. Now if it has any symmetry element, that is symmetry axis, which is Cn, the n is greater than 1 and nothing else, then it will fall into the symmetry category or point group category of Cn. If it has only sigma plane and nothing else, then it will be Cs. If it has only point of inversion and nothing else, it will be Ci. So these are some absurd point groups and some very rare common point groups. But when you have a molecule with a Cn axis and you have a sigma plane which is sigma horizontal, then the point group will be CNH. Then the point group will be CNH. Now in the same molecule, or in a molecule, if you have a Cn axis and you have a sigma v plane, the point group will be CNV. So if you have sigma h, then the point group will be CNH. If you have sigma v, the point group will be CNV. Now in the same molecule, if you have C2 axis, which is perpendicular C2 axis, perpendicular to the principal axis, then the point group will be changed to DN. Now we will not call it CN, we will call it DN. And in this condition, if it has a sigma H plane, then we will call it DNH and not CNH. Similarly, if it has if it does not have any sigma H, it only have sigma D or sigma V. So when we call sigma D, so if you have sigma V and that sigma V is actually bisecting the perpendicular C2 axis, or if in your molecule there is any perpendicular C2 axis, and if there is any sigma to sigma V plane present, then that sigma V plane is called sigma D, and the point group is called DND. Okay, if sigma H is not present. And similarly you can classify the molecule in different point groups. So if you read the rules one by one, you can easily do that. Now let us see few examples. So BF3, in case of BF3, we have C1, we have C3, we have sigma H, we have three perpendicular C2, and that because it is having perpendicular C2, so sigma V is called sigma D here, right? So the point group will be, according to our rule, the point group will be D3H. For H2O2 molecule, for H2O2 molecule, if you look at the structure, H2O2 molecule is like this and this. So in H2O2 molecule we have C1, C2 and sigma H and nothing else. So C1 is present in every molecule, and in this case the point group will be C2H. Very simple. For PCl5, again the point group is D3H, similar as BF3, and all the symmetry elements which are present in the BF3 will be present in the PCl5. For acetylene molecule, this is very interesting molecule. In acetylene molecule, C1 is obviously present. Now you have a sigma infinity axis. Why it is called sigma infinity? Because if you do as whatever rotation you do, you get similar kind of arrangement. So 0 degree rotation will also give the similar kind of arrangement, or if you do any rotation you will get similar kind of arrangement. So in this case we are dividing 360 by 0, okay, and we are getting infinity, so it is called C infinity. So C infinity axis is present, which is the principal axis, and on that C infinity axis you have infinity number of C2 axis. So yeah, so let me show you. Let's say this is your acetylene molecule, I am removing these things. Yeah, so let's say this is your acetylene molecule. Okay, so here if you rotate any degree, if you rotate, you will get the same arrangement. And now, so this is called sigma infinity, C infinity axis, which is principal axis. Now on that principal axis you can have different C2 axis. So actually you can have infinite number of C2 axis, and if you rotate along that axis you get the same arrangement. So we call it we say that the molecule is having infinite number of perpendicular C2 axis. So in and it also has a sigma plane which is perpendicular to the C infinity axis. It also has sigma D planes which are parallel to the C2 axis. So the point group will be D infinity H, right? So the point group will be D infinity H. For HCN molecule, now for HCN molecule, this side is different. Okay, so C infinity axis is there, but perpendicular C2 axis are not there. Okay, so it has only C infinity axis, and sigma V is there, but sigma H is not there. So that's why it the point group will be C infinity V. So that's how you can classify molecules in different point groups. You will get more examples in any textbook. Now our next topic is alene. This is very important. Alene is very important compound. If you understand the stereochemistry of alene, you understand the half of the stereochemistry. Yeah, so I will show you the model of alene. So this is our alene molecule. You can see this is our alene molecule. So alene is very different from ethylene. In case of ethylene, all the hydrogen atoms and the carbon atoms, they are in the same plane. But in case of alene, you can see these two hydrogen atoms, they are in a different plane, and these two, they are in a different plane. If we consider this as xy axis, then these two atoms are in the xy plane and these two are in the yz plane, so they are in the different axis. Now let us look into the slide. So in the slide we can see one C2 symmetry axis is very clear. So if you rotate the alene molecule, along this axis, yeah, so this is your axis, so this is your molecule, okay, you rotate it like this, 180-degree rotation, you get the same arrangement, right? So this is called C2 axis. This C2 axis is very much clear. So we have one C2 axis, and the sigma planes are also very clear. So you have one sigma plane along these two hydrogen atom and one sigma plane along these two hydrogen atoms. So xy plane is one sigma plane and yz plane is another sigma plane. So sigma plane is also clear. But to find out other C2 axis in the alene molecule, we have to place the molecule in a cube, which is represented at the right hand side of your slide. So you can see we have placed the alene within a cube. Now if you see, uh, here we have one axis over the cube. If we rotate the alene molecule by 180-degree, we get the same arrangement. So if we do the rotation, the hydrogen which is labeled as 1 will go to the position of hydrogen which is labeled as 3, and vice versa. Similarly 2 and 4 will exchange their places. So this is one C2 axis, and another C2 axis is actually along this, okay. So if we rotate along this also, the position will change. Now the hydrogen at one position will go to the position 4 and vice versa. Similarly hydrogen at two position will go to the position of 3 and vice versa. So these are two C2 axis which are actually perpendicular to the principal C2 axis. So there is one C2 axis which is principal C2 axis, and there are two other C2 axis which are not principal but they are secondary axis. And why the first kind of C2 axis is principal symmetry axis? Because uh, these C2 axis is actually bisecting three carbon molecules, right? So this is bisecting three carbon molecules, more number of carbon molecules it is bisecting, so that's why it is called principal axis. So now what are the symmetry elements present in the alene? We have one C2 axis, principal C2 axis, two perpendicular C2 axis, and two sigma planes, and the sigma planes are actually sigma d and not sigma h, because they are parallel to the C2 axis and not perpendicular to the C2 axis, okay. So what will be the point group of alene? Let me know in the comment section. Yeah, so the point group of alene is D to D. So this is very important. Alene is very important, and if you don't know the molecular orbital diagram of alene, I have discussed that in the previous lecture. Go through that. So our next topic of discussion is projection formula, different projection formula. Now projection formula is actually representation of a 3D molecule in two-dimensional space, because when we discuss the reaction mechanism or stereochemistry of a compound, we have to draw the molecule on a piece of paper, and piece of paper is actually two-dimensional space, but actual molecule is three-dimensional. So if you don't have a proper way of representing your three-dimensional molecule in the two-dimensional space, you cannot explain any reactivity or anything. So that's why projection formula is very important. Projection, it is projection of one three-dimensional thing in the two-dimensional space. So we have different projection formulas, but the very common and very simple one is the Fisher projection formula, which is represented here. Here we have ethylene glycol molecule. Ethylene glycol molecule is taken as a reference, and you can see the first representation is actually the Fisher projection formula. Now there are some rules which you have to follow when you represent a molecule in the Fisher projection formula. So the first rule is your near atoms should be placed horizontally. Near atom means the atoms which are towards you. So the OH and the H, the OH is one side and hydrogen is one side, and uh, they are representing like this. So they are representing towards you, or they are pointing to the eyes of the observer. they are actually pointing to the eyes of the observer. If you are the observer, they are pointing towards your eyes. So they are called near atoms, and they should be placed horizontally. They cannot be placed like this. You cannot place like this. You cannot place them vertically. You have to place them horizontally. And the rare atoms or the far atoms, uh, they are not projecting towards your eyes, and they should be placed vertically. So the two hydrogen atoms at the top and at the bottom, they are actually placed vertically. So the red representation is the Fisher projection formula of the ethylene glycol molecule. But how we see the molecule? We see the molecule like the green one, where the OH and the hydrogen, they are represented in a bold bond. Bold bond means they are towards you, they are above the plane. And the dashed bonds, that means they are below the plane, or they are away from you. They are far atoms, they are placed vertically. Okay, so this is the first rule. Near atom should be placed horizontally, and the far atom should be placed vertically. Now the next rule is the longest carbon chain should be placed vertically. The longest carbon chain should be placed vertically. So it is very important. We have this example. uh, so in this case, you can see either you can put the CHO group at the top, and then the carbon atom, and then the CH3 group, which is represented, which is correct representation. Another representation would be, you can present the molecule where OH group is at the bottom and CH3 group is placed vertically. So that is the incorrect representation, because it is not following the longest carbon chain. So longest carbon chain should always be placed vertically. You cannot place the longest carbon chain horizontally. So this is rule number 2. So from here we can decide which is correct and which is incorrect. Now the next rule is, if you have two different groups, then you have to place the more oxidized group at the top. So we have in this third rule, we have two kind of groups. One is a CHO group, and another one is CH2OH. That is, one is aldehyde, another one is alcohol. And we know that aldehyde is at higher oxidation state and alcohol is at lower oxidation state. So because aldehyde is more oxidized group, so it should be placed at the top, which is correct representation. If you place aldehyde at the bottom, this is incorrect representation according to the Fisher projection formula. Now the next rule is very very important, and that is, you cannot rotate the Fisher projection formula by 90 degree. Only 180-degree rotation is possible by keeping the molecular plane intact. So what is mean by that? So this is our molecule. If you rotate the molecule by 90 degree, you will get a different arrangement, and the two molecules are different, because now you are placing the near atoms vertically and the far atoms horizontally, which is violation of the first rule. So the first rule is, you have to place the near atoms horizontally and the far atoms vertically. But if you rotate the Fisher projection formula by 90 degree, you violate the first rule. So 180-degree rotation is possible, because 180-degree rotation will keep the arrangement same. The near atom will be placed horizontally, and the far atoms will be placed vertically. So 180-degree rotation is possible, and you have to keep the plane intact. So this is allowed. And the last rule is, Fisher projection formula, if you do a double exchange, what is mean by that? So if we do a exchange between hydrogen and chlorine, and if we then do another exchange between hydrogen and bromine, so we do a double exchange. So double exchange will give you same molecule, although you may think that the molecule in the right hand side and left hand side are different, but these two are the same molecule. When we learn about the nomenclature of stereo of optically active molecules or stereo centers, we will see these two molecules are actually different. That's why I named them R and R. So they both are R configuration, and they are same molecule. So double exchange in Fisher projection formula will give you same arrangement. And last one, which is not a rule, but you have to remember that in Fisher projection formula we represent a molecule in eclipsed form. So what is mean by eclipsed form? Eclipsed means the atoms in the carbon 1 and atoms in the carbon 2, they are in the same plane, or the angle between them is 0 degree. theoretically 0 degree. So this is called eclipsed form. There is another form called staggered form, where the angle is around 60 degree. So we will learn about this eclipsed and staggered more when we will discuss about the conformational analysis of the molecule. So this is all about Fisher projection formula. You have to understand all these rules. Okay. Now the next thing. Now the next thing is there are three more projection formulas, which are Newman projection formula, Schauer's projection formula, and flying wedge projection formula. Okay, so these three are also very important, and you can see these are the representation of this all these three projection formulas. So actually the projection formula is how you look at the molecule. The molecule is same, but how you look at the molecule and how you draw it in the paper, that is the difference. Okay, so in the Newman projection formula, we look at the molecule we look at the molecule from this point. So if you look at the molecule from this point, from here, this is Newman projection formula. Okay, you can see. Now if you look at the molecule like this, slightly tilted, okay, then it is Schauer's projection formula. If you look at the molecule from the side, okay, then it is flying wedge projection formula. So you can practice it with your pen and pencil, and you will be master in that. Now we will see how you can convert one projection formula to another. That is very important. If you cannot convert one projection formula to another, you cannot solve a single problem in stereochemistry. This is very important. You have to learn it. So first you have to look at the molecule in the correct way. Okay, so the Fisher projection formula is the red one, but how we have to look at the molecule is the green one. One thing you should remember is the green representation is just for your understanding. This is not any proper representation. Okay, it is just for your understanding. So first step is you have to draw the molecule in the Fisher projection formula, but here we are drawing it in the green representation, because we have to look into the molecule like this. Now identify the carbon skeleton. So this is our carbon skeleton. So we just make a tilted bond. The carbon skeleton, and now we can see the OH groups and the hydrogen atoms, they are above the plane, they are at the top. So we make them top. Okay, OH and hydrogen, we make them top, and the methyl groups, they are below, so we make them below. And this is our Schauer's projection formula. So very easily you can convert from Fisher to Schauer's if you know the way of how to do it. Now it is actually representing the molecule in the uh, eclipsed form. What is eclipsed form? So this is our molecule. So you can see this hydrogen atom and this hydrogen atom, they are in the same plane. The angle between them is 0. Between this atom and this atom, the angle is 0. Between this atom and this atom, the angle is 0, right? So this is called eclipsed. Now if you rotate, now the angle becomes 60 degree, and it is called staggered. So if you just rotate the structure, you will get the staggered form. Okay, so this is how you can interconvert from Fisher to Schauer's. Now the next is Fisher to flying wedge. Again you have to identify the skeleton, and now you have to look from the side. So in the previous case, that was a tilted view. Now you have to look from the side. And if you look from the left hand side, how you will see, that the OH groups are at your near side, and the hydrogen atoms are far from you. So you just and the methyl group is below. So first we make the methyl group below. So first we look at the skeleton, we make a parallel bond, and now we make the methyl groups below, because they are below. So this is very simple. Now hydrogen, we are looking from the left hand side. So hydrogen is the OH groups are towards us, so we make OH group towards us and hydrogen away from us. Yeah, so this is very simple. So this is again the eclipse conformation. If we rotate it, we will get the staggered form. So again you can do it very easily. Now the next thing is Fisher to Newman. Okay, so in this case also you have to look into the skeleton first. Now the way of doing it in the Newman projection formula is little bit different. You have to look into the molecule in two halves. First is bottom half, and the second one is the top half. So we first draw the bottom half. We first draw the bottom half and we make it front carbon atom. So we have drawn the bottom half and we make it front carbon atom. So you can see the OH group is at our left hand side, and it is above. The hydrogen group is at our right hand side, and it is also above. The methyl group is below at the bottom. Now we have written the below part. Now for our top part, we can arrange them accordingly. So OH, the top OH will be same side in the bottom OH, and similar will be for hydrogen and methyl. So we do that and we get our Newman projection formula. Again, it is in the eclipsed form, so if you rotate you will get the staggered form. Okay, so this is also very easy. So these three conversion is very easy, and the last conversion which I will show you is the conversion from Newman to flying wedge. So this is our Newman projection formula. So in this case you have to first distinguish between carbon 1 and carbon 2. You first make carbon 1, and if we look at the molecule, you can see methyl is at the top, hydrogen is at our right hand side, and OH is at our left hand side. So we make hydrogen towards us and OH away from us. Now we make the second carbon atom, and we have this. So now you make the ethyl group which is below, and hydrogen is at your right hand side, and methyl is at your at your left hand side. So this is the flying wedge projection formula. So these are some tips and tricks how you can interconvert from one projection formula to another. So here we come to the end of this lecture, and so this lecture is foundation for our course what we will learn in the next lectures. So this is very important. I hope I am able to make you understand all the topics. If you have any confusion left, let me know in the comment section. Thank you for watching.